All right, so this last section in chapter 7 that we're going to cover, we're going to skip over 7.5. So section 7.4 is estimating the population proportion with confidence intervals. So the main thing here is we want to be able to use the central limit theorem to construct what we call a confidence interval for a population proportion. All right. So here's an example of the Affordable Care Act with birth control. So the Kaiser Health Tracking Pool surveyed 1,504 American adults and asked them if they supported or opposed the requirement that private health insurance plans cover the full cost of birth control. The poll found the 61% of respondents supported this requirement. So what we're asked is, what percentage of all Americans can support this requirement? So from previous sections, we know our estimator p hat is unbiased, right? And the population parameter would be very close to 61%. So my standard error can be estimated using p hat instead of p. So if I plug p hat in there, I'll get a standard error of 0.0126. So, and also, because the sample size is very large, the probability distribution of p hat is approximately normal and centered around the true population proportion. Right? So, there's about a 95% chance that p hat is closer than two standard errors away from the population proportion. Right? So, it's within two standard errors. Right? So if I find two standard errors, we get 0.0252. So now if I take my mean, which was 61%, and subtract and add 2.5% to it, then this would be my confidence interval, right? So we're 95% confident that the value of the population proportion is within 2.5 percentage points of 61, right? So it's in between 58.5% and 63.5%. Right? So this is what we call a confidence interval, right? So we're trying to build this. So you're trying to find what two values make up where the two standard errors are, right? So confidence intervals provide us with two things. One, a range of plausible values for a population parameter, and two, a confidence level which expresses our level of confidence that the interval contains the population parameter. And 95% confidence intervals are very common, but we can do multiple different ones, right? So a confidence level tells us how often the estimation is successful, and also measures the success rate of the method, not of any one particular interval, right? So another topic we can talk about is margin of error. So margin of error is the value that we're adding and subtracting from the mean, right? So this tells us how far from the population value our estimate can be. So to find the margin of error, we're going to take C critical times this standard error. So this Z with the asterisk, we call that Z critical, right? So Z critical is a number that tells us how many standard errors to include in the margin of error. So from the empirical world, we know that a Z score of 1 corresponds with a confidence interval level of 68%, and a Z score of 2 corresponds with a confidence level of 95%. Right? But actually, we can be a little more accurate, right? So like we were saying, 95% is about 2 standard deviations away, right? But to be even more accurate, it's actually 1.96. So this table can provide us some z-scores to use to be more precise, right? So if we want an 80% confidence interval, we would use a z-score of 1.28, and 90% confidence level, we would use 1.645, and so forth, right? So this table will come in handy, right, when building confidence intervals. So in this table is also in the appendix of your book, right? So confidence intervals have this form. You're going to take p hat plus or minus the margin of error, right? We're letting m represent that, right? And if instead of margin of error, if you want to write that as z critical times the standard error, that's fine too, right? So you can also write it as this equation. And typically, we're not going to know what p is, right? So if p is unknown, we're going to use p hat to estimate, right? So here's a standard error estimate. So plug p hat in instead of p, right? So here's an example. It's titled Intelligent Life on Other Planets. So a Huffington Post YouGov poll of 1,000 Americans found that 38% believe that there is intelligent life on other planets. So we want to construct a 95% confidence interval for the percentage of all Americans who believe there's intelligent life on other planets. And B, would it be possible to conclude that 40% of Americans believe in intelligent life on other planets, right? So we need to check the conditions of the central limit theorem still, right? So I have a p hat of 0.38. So one, we do have a random independent sample, right? Number two, do we have a large sample? And we do, right? If I take n times p hat or n times q hat, I get some large values, right? That are greater than or equal to 10. And we would assume here that the population would be at least 10 times greater than my sample, right? Because the population here would be all Americans, right? So we can definitely assume that there's more than 10 times 1,000, right? So more than 10,000 Americans. So we're good with all of those criteria. So in order to find the confidence interval, first you want to start by finding the standard error, right? So we're going to plug in p hat, plug in n. You should get a standard error of 0.0153. So then my margin of error, I take the z value, right? So since we're doing a 95% confidence level, the z-score from that table was 1.96, right? So typically we just say 2, but 1.96 is more accurate, right? So in doing so, we get a margin of error of 0.03. So if I take 0.03, add, subtract it to the mean, then I get the confidence interval, right? So this is referred to as the lower part, and this is the upper, right? So values in between. So I would expect 95% of my data to be in between here, these two numbers, right? So we have a 95% confidence interval is 35% to 41%. So it is plausible that 40% of Americans believe in intelligent life on other planets, since 40% is in between this interval, right? So I'm 95% confident that we're going to have some percentage in between 35 and 41. So since 40 is in there, it seems plausible, right? So if it was outside of this range, then the answer wouldn't be no, right? It would not be plausible. So if you want to do this on the TI calculator, you can follow these steps and use this command, right? So if I go back to this this example, I can go to second. Oops, first we gotta turn it on. So we go to second distribution, and then go down. Whoops, did the wrong button, right? We need to go to stat, and then go over to test, right? And then I think it's like option B. No, A. So we want a 1 prop z interval, right? So hit that, and then now it's going to ask you your x value, your n value, and your c level, right? Your confidence level. So I know this is 0.95, right? So to get these values, let me go back to the original. I think we were given those, right? So well, n here would be 1,000, right? 1,000 Americans. And my x value would be 38% times 1,000. So that would be 380, right? So put 380 in here, and that should do it. Oops. I must have hit enter too much. Too many times. Let me see. So we are on option A, right? So my values are still saved. Calculate. There we go. Now I have those values. So if we go back to the problem, we want it in between 35% and 41%, right? So if I round those, that is accurate, right? So your calculator is going to be a little more accurate than doing this calculation by hand, right? So that's one easy way you can do that. So here's another example, an election prediction. So a political consultant randomly surveys 300 voters in a district to see how many intended to vote for a certain candidate. Of the 300 voters surveyed, 165 indicated they will vote for the candidate. Using a 99% confidence interval, should the consultant predict that the candidate will win the election? Why or why not, right? So if I go back in and go to my stat menu, go to test, and then go down to option A, right? The 1 prop Z interval. So my X value here would be 165. My N is 300. My confidence interval is 0.99. I can go to calculate, and there's my interval, right? So let's go to the next slide. So with this next slide, I calculated this. Well, first we gotta check all of the requirements for the CLT, right? All of our assumptions. So one, we do have a random independent sample. Check now. You need to check your sample size. So we take n times p hat and n times q hat. See if that's greater than or equal to 10, which it is. And then we could assume that number of voters is greater than 3,000, right? So we're good there. So we meet all of our conditions. So then now we can go in and calculate the 99% confidence interval, right? So I did the same steps by hand, and my calculator agrees, right? So since the interval contains plausible values that are less than 50%, the consultant might not predict the candidate will win the election, right? So what we're saying is my confidence interval does contain values that are less than 50%, right? So in order for someone to win an election, they have to be bigger than 50%. So we can't exactly conclude that, right? So that the candidate could lose, right? So then here is just a printout from StatCrunch, right? And it has a lower limit, upper limit here, just as we calculated over there. Right. So you can see this also calculates p hat, the sample proportion, right? So one thing I do want to point out, as if you notice, and this makes sense, right? The wider that we go with my confidence interval, the more confident that we can become that I'll have, my true value within this range, right? So like 68% is smaller than 95% confidence interval, right? 95% confidence interval is smaller than a 99.7% confidence interval. So the higher the percentage of confidence, the wider the confidence interval, right? So that's just a visual to help you understand that relationship, right? All right. So that's all I have for this section. So that should get you through the homework. Okay. Make sure you email me if you have questions.